Stanford University.
So lecture 4, CUDA memories. So I thought what we do is just go around the room and reminisce about some anecdotes from MP1. No, not really. So we're going to talk about the different CUDA memory spaces which CUDA exposes to the programmer. So, you know, in a normal C or a C++ program, there's not really this notion of several memory spaces that you have to really keep track of, right? So a pointer is basically a pointer as far as the programmer is concerned. You can, you know, dereference a pointer wherever you want. You can write to a pointer wherever you want. It doesn't really matter, you know, what function you're in or what sort of context you're in, because there's not this notion of a partitioned memory space. But CUDA sort of introduces that idea to sort of expose the different kinds of parallelism and performance that's available on the GPU. So let's just dive right in. And so, you know, in the previous few lectures, we've been sort of given these high-level block diagrams of the GPU or you know, a kernel launch to sort of give you an idea of how memory and computational resources are actually laid out on the GPU. And so, you know, just to refresh your memory, the GPU is basically this collection of streaming multiprocessor cores, right? And each one of these multiprocessors has some finite number of registers that it can write into, and these exist actually on the silicon right next to the computational resources. They're very fast, and each thread can read and write to those registers. In addition, CUDA sort of exposes this idea of a local memory. And so this name is kind of actually a bad name, because the memory isn't actually local to the actual chip at all. In fact, it's actually implemented in off-chip global memory. But the reason we call it local memory is because each CUDA thread has private access to it. And so you can't actually communicate through this memory, but it's sort of a large address space that each thread can sort of index dynamically and write to it privately. But it's actually a very slow memory. And so sort of moving up the memory hierarchy, we have this idea of a per block shared memory. And so the reason this sort of shared memory is interesting is because it sort of allows this intra-block communication, right? So this is sort of a memory space that different threads in the same block can use to talk to each other in. And this is very important because, you know, as David has been reminding us in the last few lectures, you know, ordinarily threads in different blocks, they don't get to talk to each other, right? Because there's no guarantee on the ordering that those blocks are going to get executed. So you don't really have any guarantee that, you know, a thread in block 0 is going to be able to communicate with a thread in block, you know, 13. But what shared memory allows you to do is basically localize the threads that need to talk to each other into a single block. And this is sort of the address space and the memory resource that they can use to talk to each other. And so this shared memory is actually implemented in the same silicon as the you know, registers and streaming processors. So it's very fast. It's actually, the latency to this memory is comparable to the latency to registers, basically. So it's very fast, and, you know, it allows very low latency communication, but only within a thread block. And then, of course, moving up the memory hierarchy, we get to this global memory address space. And this is actually the memory that you're allocating, you know, in MP1 when you made calls to CUDA malloc. So this memory is stored off-chip. It's basically stored in DRAMs. And the latency to it is very high compared to these other address spaces, basically 100 times slower, let's say, than access to registers or shared memory. But of course, the upshot there is you get a lot of it. You know, you can buy GPUs with gigabytes of memory. So, you know, global memory is this huge address space that you get to work with, but the latency to it is very high. And then finally, we have this idea of a constant memory address space. And the idea here is that you know, GPUs ordinarily don't have big caches because they're sort of complicated to implement. They require lots of transistors, lots of die area, basically, so they're very expensive. But the nice thing is if that you don't require a sort of read-write mechanism to the memory, if the memory is just constant, if it's read-only, you can actually implement a very simple kind of cache to speed up that memory. And so constant memory is this address space that basically gives you a lot of memory that all threads have access to, and it's cached, but you can't write to it. You can only read from it. And so let's take a look at how that's actually implemented in the language. And so basically the way that you get access to these memories is to sort of annotate your variable declaration with these new little keywords. And so you know, we can just start at the top of the table here. Ordinarily, if you just declare a variable in your kernel, like int var, well, this is just like a normal C variable. It's going to be put into a register. But the only difference here is that the register is going to be on the GPU instead of the CPU, of course. And so register variables, the scope of these variables, or the lifetime, is just a single thread. So a single thread has access to these variables, and you get one of these variables per thread. So you can think of hundreds of thousands of these register variables. So sort of moving up the hierarchy, you can actually create arrays of these per thread variables, like I've done here, int array var 10. And so when you actually make an array like this, what the compiler is going to do for you is to put this into this per thread local memory. And remember that this memory is going to be slow, but the upshot is you get quite a bit of it, and you can also sort of dynamically address it. Right? You can create arrays and you can index it dynamically. And again, this has the scope. These arrays have the scope of a thread, and they're private to each different thread that you launch. So moving up, the way you create one of these shared variables that the entire thread block has access to is you just sort of annotate it with this little keyword shared on the front of the variable declaration. And so this is going to be put into, literally shared memory that exists on the actual silicon die right next to the streaming multiprocessors. And so the scope of these kind of shared variables, that is, who has access to it, who can see it, is the entire thread block. So the lifetime is going to exist over the course of the entire thread block. It's not like a private local variable that only a single thread can see. And then finally, moving up, the hierarchy, we can create these global variables that exist in the global scope, just sort of like in C, but you can prefix them with this device annotation to say, okay, put this in the global memory space. Everyone can see it, but access to it is going to be pretty slow. And so you can basically do this sort of thing if you don't want to deal with dynamically allocating this memory with CUDA malloc. You can just create a global variable with the device tag there. And then finally, it's pretty simple. For a constant variable, you put these in the global scope. You name them with the little constant there, and this will create a constant that all the threads in your grid launch or your kernel launch can see. And it will have the scope. The scope of these variables will be, the entire grid of threads can see it, and it will have the lifetime of the application. So the variable will come into life when you start your program, and it will go out of life when you end your program. And so this kind of just reiterates where each of these variables are stored. Just normal automatic variables like int var that goes right in the register. And the sort of relative performance of access to these variables, we'll just say is 1x. So it's very fast. Or I should say that the penalty of accessing these variables is small. It's just 1x. But if you go and say, actually, I need an array of these variables for each thread, so that's going to be put into local memory, and then access time to this array is going to be very slow. So we're actually going to suffer something like a 100x performance penalty because this array is actually implemented in memory that is not on the silicon. It's actually stored off chip. And then again, shared variables go right into the shared memory address space, which is very fast, almost as fast as registers. So there's not really a performance penalty there that you ordinarily need to worry about. And then, of course, a device variable or a global variable, again, gets put in the global address space. Everyone has access to it, but latency is going to be very high, around 100x. And then finally, constant variables actually get implemented in the global memory off-chip address space, but they're cached on chip. So ordinarily, you don't have to worry about performance to these kinds of variables. They're basically going to be on the same order as accessing normal register variables and shared variables. And so you can kind of compare the scale of threads that can actually see these variables. So when you ordinarily create one of these automatic register variables, you're going to create hundreds of thousands of these, right? Because you're going to have one per thread. But the visibility of each individual variable is just going to be one thread can see it because it's private. And that's the same with these arrays that get implemented in local memory. But then with a shared variable, since these actually have the scope of a block, and then every thread in the block can see it, that means you're going to be basically instantiating several orders magnitude fewer of these, right? Because you'll have basically one of these variables per block. But then on the other hand, hundreds of threads can see it, right? Because thread blocks have the size on the order of hundreds of threads. And then of course these sort of global device and constant variables, basically for every single one of these instances that you make, hundreds of thousands of threads can see it because everything in the block is able to access them. And so you might ask, well, where do you actually declare these variables? So it depends on basically whether or not you want the host to access it and which threads in your which threads in your grid you like to access it.
So I was wondering if you have like a one element array, would it be treated as global or would it be treated as a register?
So the question is, what happens if you have a one element array?
So if we use pointers.
So well, it depends on what you're pointing to, I guess, is the correct answer. And I'll sort of get to that. But ordinarily, if you were to go to, let's say you create an array of 10 elements per thread, right? So the compiler has a little bit of discretion on where it's going to actually implement that array. So ordinarily, if you're going to dynamically index that array with indices computed at runtime, it has to put that in local memory because registers can't be indexed. It's just physically impossible right now given the architecture. But if you access the array using indices known at compile time, so statically indexing, then the compiler can actually put those into registers.
Yeah, I wonder if we can get around it by pointers.
So no, I mean that doesn't really get around it, right? You're still pointing at something, and so the problem is you have to figure out where you have to follow that pointer to find out where the memory actually lives.
So basically, whenever we make a pointer, then it's already global.
Or yeah, so far, in the MPs, for example, you've got pointers. They point to global memory. They've been allocated through malloc or something, right? So those are all implemented in global memory. Right. Yeah, and so basically, if you want to declare one of these constant or device global variables, stick those outside of any function in the global scope. If you want the kernel to access it, these things go inside the actual global function or the device code. So let's look at some code examples. So this is just a short example of how these thread local variables or register or array variables would work. And so to motivate this example, this is kind of a simple k-nearest neighbors code. So the idea here is that we have some set of points, call them p, and some set of points, call them q. And for each point in p, we want to find the 10 nearest points in q that are actually nearest to that point. Right? So you can think of implementing it like this. So basically the idea will be to parallelize over the points in P. So these are the points that you actually want to search nearby. So each thread would read in a point, call it P, and that will just go in a register variable, right? And so to find the closest points in Q that are closest to P, the idea would be for each of these threads to read through this Q array into this local heap structure that's stored in local memory. And then it's basically just a matter of pushing and popping to this heap to find the 10 nearest neighbors to P. And the complete code for this example is on the the website. This is just sort of a straw man to show you the difference between register variables and these array variables. So this is a slightly more interesting example of how to use shared variables. And to sort of motivate this example, I'm going to implement this simple algorithm. I'm going to call it adjacent difference. So you can think of this algorithm as computing some sort of approximate derivative. So for each element in an array, I'm going to compute the difference between that element and the previous element in that array. Okay? So here's a naive way to do that without using shared memory. All right, so we start up at the top, as we usually do, by computing the index, the global index of the thread that we've launched. And then if I'm not the very first thread in the launch, I want to compute the difference between element I and element I minus 1. So that's pretty easy, right? We just read in input I and input I minus 1, and then take the difference and store that to the result. And so, you might start asking some questions. What are the bandwidth requirements of this kernel, right? So let's just look at the loads. Let's look at all the loads from global memory that this kernel does. Well, we've got one here, right? We read input of I, and then we read input of I minus 1. So right now we're doing 2 loads from global memory to implement this kernel. Then you might, there's the 2 loads. We'll ignore the store for a second. Then we might ask, well, how many times does this kernel actually load element I, right? Are we doing anything redundant? So we load element I once by thread I, but then we load it again by thread I plus 1. So we're actually doing a lot of redundant work here, right? We're doing twice as many loads to the kernel as we actually need to do. So the idea is going to be, well, we want to eliminate this redundant load using shared memory. And basically what we're going to do is allow the thread to cooperate such that we're not doing any redundant work. And we're going to do that with shared memory. And so here's a slightly more sophisticated example of doing that, and it's going to span a couple of slides. So first, I'm just going to start out with some shorthand for threadindex.x, just so everything fits nicely on the slide. And then next, what I'm going to do is I'm going to allocate a shared array called sData across the entire block. So even though we've put this variable declaration inside the global function, it might look like every thread has a copy of this variable. That's actually not true because we've annotated it with this shared notation. So this sData, this array can be seen by every thread in this block. And so what we're going to do, we're going to start out by loading element I from the input. And that's pretty simple. We're going to put that into this shared array called sData, and that's just sData of tx equals input I, just as normal. We just do a load and store it into the array. But what we've run into here is a race condition if we go on any further, right? Because we need to wait for everyone in the thread block to load their element into the shared array before we can continue, because otherwise the data won't be ready for using in the computation. So what we do is just insert a barrier there called sync threads. And you can think of a barrier, it's pretty simple. Just think of it as a race to get to the bottom of the code here. And basically what has to happen is that every thread in this block has to get to the sync threads before any of them is allowed to continue. Okay? And so just inserting this barrier here,
The sync barrier ensures all the thread in my block or globally synchronized?
The synchronization happens, so the question is, who synchronizes on the sync threads? It's all the threads in a single block, right? Because we can't do global synchronization, if that makes sense. Okay, and let's look at the second half of the kernel. It's very simple. Instead of reading from the global array, we're just going to read from the shared array like we would any other pointer. And it's just the difference of the index or the element I loaded and the element my neighbor loaded. And then at the end, we have to handle this weird corner case that happens on the boundary of the block and actually do that one redundant load from the input. And this sort of happens because shared memory doesn't span multiple blocks. And so you might notice that in this previous example, I've size this array S data with a constant, this block size constant. Well, what happens if I don't know how much shared data I need to know at compile time? What if I need to know it at runtime? Well, that's pretty simple. You can actually dynamically allocate shared memory at runtime by using this extern notation that's sort of appended to the declaration of the array. And then when you launch your kernel, you can pass this third argument to the triple chevrons there to say how big the shared array needs to be. So you don't necessarily have to know how much shared memory you need at compile time. You can dynamically allocate it at runtime before you launch the kernel.
Could you declare two things like that?
So you can't actually add extern to more than one array, but there's kind of simple workarounds. You can have different pointers to the shared memory and do it all that way.
Is that same thread equivalent to the CUDA thread synchronize?
It does something similar. It is not equivalent. So the CUDA thread synchronizes the host, or the CPU, with basically the GPU. And the sync thread synchronizes all the threads in a single block. So we can kind of analyze the optimization we've done here and just tabulate and go down the table. In the original implementation, we can look at the number of global loads we did, so the number of times we read those array elements. And that was two in, right? We did all this redundant work. But in the improved implementation, we do n plus n over block size global loads. So we've substantially reduced the loads that we're doing from global memory. And then we can actually measure the throughput of the two different implementations, and you'll see that the relative improvement is basically 1.5. So it's pretty decent for the amount of work that we put in. But if you look at it on an improvement per line of code basis, we're probably only at 0.8% improvement per line of code. And so I guess the point I want to make here is that these kind of sort of optimizations usually come with an implementation cost. And so before diving into some sort of optimization, you should really think about whether it's worth it. And whether it was worth it for this particular problem is up for grabs. And so let me just say a few words about pointers in kernels. So yes, you can use pointers, obviously, but you can also point to any memory space per se, basically, that you want. So in this foo global function, we can declare pointers to a global variable. We can declare pointers to constant variables or shared variables, and you can read and write between them. But just to note that pointers aren't actually typed on a memory space, so the space is not part of the type. And so what does that actually mean? So if I declare this shared int star pointer, you might ask, well, where does pointer point? So in this sort of declaration, note that the actual variable pointer is shared. It's not that we're pointing to another variable in the shared space. So that's just a note that you should make in your sort of mental model of what's going on. And then finally, please don't confuse the compiler because it will make your life miserable. So let's take a look at some code here. So in this code, I've got I've got a global variable, my global variable, and I've got a shared variable, my shared variable, and I do some pointer arithmetic, right? So at the end of this code, where does pointer point? Does it point to the global memory space, or does it point to the shared memory space? Right? The compiler can't prove it because it depends on what happens at runtime. And so probably what's going to happen is that you're going to see a warning like, I can't tell where this pointer points to, be careful, you might be running into some problems. And indeed, if you compiled and ran this code, it would probably crash, just simply because the compiler could not figure out which memory space to implement this a store in. And so just some advice when using pointers. Prefer to dereference pointers in regular access patterns, sort of like the access patterns that we've shown in the tutorial codes. Basically, every thread, for optimal performance, every thread should access basically a pointer contiguous with his neighbors in his block, if that makes any sense. So you should try to access pointers using functions, simple functions of the thread index. And avoid propagating pointers and making pointers to pointers. Basically, the GPU would rather not pointer chase. It would rather not chase down linked lists and trees. The memory subsystem is just not built to do that, although it can do that. It will not do that in a way that's high performance. So things like linked lists are not going to perform well. And then again, pay attention to the compiler warning messages. The last example will output this warning. I can't tell what the pointer points to. I'm just going to assume you meant the global memory space. And so if it assumes wrong, you're probably going to cause a crash. So a common programming strategy, if we can generalize from that adjacent difference example, is that I should declare my problem set basically in the global address space, using CUDA malloc like we have been doing. But then what I want to do is tile up and partition that data in global memory into these decently sized blocks that we can fit into shared memory, because that space is much faster. And then basically divide and conquer to implement our algorithm. And I'll show you sort of a graphical example of what I'm talking about. So up here, sort of visualized in the cloud, we've got this global memory, some input or an array or something that lives in global memory. So what we want to do is partition that data into subsets that are going to fit into shared memory. So we've just divvied up our big global array into these smaller subarrays. And then what I'm going to do is handle each one of these subarrays with an individual thread block. So here I've got some thread blocks. They've got 4 threads running in them. They've got this orange shared memory space that they have fast access to. And so what I'm going to do is basically in each of these subsets, I'm going to load this small partition of data into the shared memory using multiple threads, like we did in the adjacent difference example. And we want to basically do this to exploit a memory level parallelism. And then once that data is on the fast shared memory inside the block, we're going to perform whatever computations we need to do on the subset just to and fro that shared memory access space. Maybe using sync threads if we need to synchronize. Maybe using the atomic operations if we prefer to do that. But the point is, this is a much faster way to access your input. And then finally, at the end of the day, we're going to copy that result from shared memory back into the global address space. And so, basically what you want to do here is partition your data according to the way you'd like to access it. If you just need read-only access to the data, that ought to go into one of these constant memory variables because they're fast. If you need to read and write the data within a single block, that needs to go into shared memory because it's fast and it's going to allow threads in the block to communicate with each other. But if you don't need that communication, you don't need any of these annotations at all because they're going to just go into a register or a local memory variable. And then finally, as should be obvious by now, we're going to use CUDA malloc to allocate space to hold our input and output to our kernels. And so let's just take a look at communication through shared memory. This is going to sort of reiterate the point that David was trying to make last time about race conditions. So say I've got this global function called race, and I've declared this shared variable that everyone in the block has access to, and I just write my thread index to it. So after I do that, what is the value of my shared variable? Of course, we have no idea, right? Because this is a race condition, and the result is actually undefined. So in order to have some proper semantics and a well-defined value for that result, we need to use either barriers, such as sync threads, or atomic operations to enforce these well-defined semantics such that we can actually reason about the value of these variables. And so this is basically how you would implement that kernel using a barrier. So we've declared this shared array data. It has the size of the block, so every thread in the block has basically a slot in that array. After we've written into that array, if we call sync threads, then after that barrier, basically the state of that array is well defined. We know what the state of that array is going to be. And of course, the alternative here is to use atomic operations if we don't know exactly what our memory access patterns are. And so David showed us some examples of atomic access to global variables last time. You can do that the same way to shared variables. And after this kernel, say we want to compute the sum, since we're using these atomic adds, we'll have the sum of the entire array after the kernel exits. But you might ask the question, how many threads are actually going to compete to get access to that result variable that we're accessing atomically? So say we launch a total of n threads. That means n threads are going to compete to try to get to access to that variable using the atomic operation. And as David reminded us last time, that's going to serialize our algorithm as all the threads line up and try to add to that variable atomically. So we want to avoid this sort of operation. And here's a decent way to do it. So you can actually make a hierarchy of these variables that you want to access atomically to implement things like sum. And again, we're going to use this divide and conquer idea to parallelize our data as well as our algorithm. So up here in the global, say we want to compute the sum of a large array. So up here in the global address space, we've got this single variable. Let's call it sum, right? That's going to store our result at the end of the day. And what we're going to do is going to launch several thread blocks. In each one of these thread blocks, we're going to have a single shared variable that's available to them. Call it sum sub I, sum 0, sum 1, up to sub n. These are going to be partial sums computed on a per block basis. And so the idea is that we're going to first atomically update the shared variable that exists per block. And then at the end of the day, we're going to take that result and update the global variable. And this is going to reduce contention on that global variable so it's not so serialized. And so this is what it actually looks like in code. So to start off, we declare this shared variable partial sum. The entire block has access to this. And we're going to make it thread 0's responsibility to sort of initialize that sum to 0. So what we do is check, am I thread 0? OK, if I am, initialize partial sum to 0. Everyone else in my block has to wait because I've got this sync threads here, this barrier. So after that sync threads, we've initialized the partial sum to 0. And then after that, it's pretty simple. Every thread in this block is going to read from the input and atomically add to the partial sum. So we're going to compute a per block partial sum for each one of our thread blocks. And after we've done that for each thread in the block, we call this sync threads barrier to make sure that the partial sum is ready before we continue on. And then finally, it's poor thread 0's. It's his job to update the final total sum using the partial sum that we computed per block. And so you can ask, well, what is the scale of contention for that result variable, and what is the scale of contention for the partial sum? Well, if, say, each one of our thread blocks has 4 threads in it, only 4 threads are going to compete when the atomic add happens to the partial sum. And say we launched 10 blocks. That means only 10 threads are going to compete for access to the total sum at the end of the day. So we've sort of transformed our contention problem from one of size n to one of size n over the number of blocks that we launched. So that's just a nice way to divvy up the problem. And actually, you can do even better and have multiple partial sums per block to reduce the scale of contention even further. So just some general advice. Basically, use barriers like sync threads to wait until data in shared arrays are ready. And what you should do is prefer to use sync threads and barriers to atomic operations if you can predict beforehand your data access patterns, if they're going to be regular. That implies that you need to use a barrier instead of atomics. And then when your data access patterns are maybe sparse or unpredictable, that implies that you want to use atomic operations. And then finally, atomic operations to shared variables are going to be much faster than to those to global variables, just because the latency, the time is much faster. So let's take a look at slightly more complicated example. This is matrix multiplication. So this is basically bread and butter of high-performance computing, right? Everyone wants to multiply dense matrices together. So here's one way to do it in CUDA. And this is also basically, I think, our first look at sort of optimization and thinking critically about the performance of our kernels. So the basic idea here is we're going to do something similar to what we did in adjacent difference example. Basically load tiles of the data into shared memory, work on those tiles, and then write out to global memory. And so just recall that in dense matrix multiplications, for each element of the output, so AB sub ij, basically the result or each element is a dot product between an entire row of say A, an entire column of B. So we're going to implement a bunch of dot products on the GPU. And so what we're going to do is our parallelization strategy will be to launch one thread for each result of the output. Okay? So basically each thread will be responsible for one dot product, one of these very large dot products. So here's basically a first implementation. We're going to launch a 2D kernel just because it's kind of convenient, right? And we're allowed to do that. And we're going to calculate the row and the column indices of our element that our thread maps to in the result. And this is that basic computation that we're always doing in our global functions, but we're doing it in 2 dimensions. So we've got row and column indexing the output. So we're going to allocate a register variable, call it result, and initialize it to 0. And we're going to be summing up a bunch of multiplies into this variable. And then finally, we're just going to implement the dot product with a for loop in the kernel. That's perfectly fine to do. We're allowed to use for loops in a kernel. And basically just, it's pretty simple. We do a multiply and an increment to that result variable to implement this dot product. And the indexing happens into A and B according to the row and the column and the size of the matrix. And then finally, at the end of the day, we're going to write out the result to our result to the AB matrix. So it's pretty compact code, very simple and straightforward. But we should ask ourselves, well, how will this actually perform? And so we can actually tabulate the process or the thinking process that goes into figuring out what this kernel is actually doing. So let's start at the top. How many loads do we have to do from global memory per term of the dot product? And that's basically 2, right? If we go back to the slide, we have to load from A and load from B for each term in this dot product. And that's 8 bytes if we're doing single precision. And then we might ask, well, how many floating point operations do we do? And that's just 2, right? So in the dot product, we do interesting. Okay, here we go. So in the dot product, we do a multiply and an add. So that's 2 floating point operations per term. So what we're going to ask ourselves is, what is the ratio of the bandwidth to the actual computation that we're doing? And that's pretty simple. We're just going to take those 8 bytes that we load per term and divide it by those 2 operations, and that gives us per floating point operation we need to load in 4 bytes. So now we know the basic, bandwidth constraints of our kernel, and we can ask ourselves, well, say we're working on the GTX 260 that are in the PUPS cluster. What's the peak floating point performance that is reported for these cards? And it turns out it's around 800 gigaflops. And so if we take that peak performance, we can ask ourselves, well, how fast does my bandwidth need to be to actually saturate that peak performance and to make sure I'm actually getting the bang for buck, out of my GPU? And to find that, we just take this, this ratio of global memory accesses to flops and then multiply it by the peak. And what that tells us is that we actually need 3 terabytes per second bandwidth to feed this kernel. And then you might ask yourself, well, what is the actual peak bandwidth of this card that I have? And you realize, actually, it's only 100 gigabytes per second. And so at this point, you might be asking yourselves, who would ever design a GPU this way, right? Why would you only give me, 100 gigabytes per second if my peak floating point performance is something like 800 gigabytes. How am I supposed to feed this card with this measly bandwidth you've given me? And so you can actually take a look at what the upper bound of performance is for this kernel that we've just written, and it turns out it's only 28 gigaflops, and that's incredibly depressing, right? Why would they design a card this way? So the answer is that GPU architects were betting that we wouldn't be stupid enough to write that last kernel. We've actually got more resources in the language and the GPU to deal with, and we can actually increase the effective bandwidth of the kernel. And so the idea here is to basically do what we did in the adjacent difference example, and to give us more effective bandwidth by using that shared memory. So what we realize is that while each of these input elements from A and B is read redundantly, again, by a number of threads that's equal to the width of these kernels. So we're doing all these redundant loads that we could probably get rid of if we were just a little bit smarter. So our basic strategy here is going to be that we're going to load each element from A and B into shared memory, and several threads are going to be able to use that from that fast shared memory space, okay? And to basically do that, we're going to partition our loop, our kernel loop, into phases of operation. And so the idea here is that we're going to load a tile of data from both A and B into the shared memory space. We're going to do that once per phase. And then each phase, each thread is going to produce a partial result. And basically, as we iterate over phases, finally we will have a final result at the end of the day. Okay? So let's take a look at a slightly better implementation. So we basically start out just like we did before. Each thread of the kernel launch is going to correspond to a unique element of the output. Okay? And to do that, I'm going to use some shorthand for thread index and block index just so it fits on a slide nicely. And so what we're going to do is we're going to allocate some two-dimensional shared arrays that the entire block is going to get to share and have access to. And we're going to take those tiles from the input matrices and load them into these shared arrays in parallel. So let's take a look at what that looks like. So we start out by putting this, creating this for loop that wasn't in the previous kernel. And basically this for loop is going to loop over these phases of operation. So we'll loop from phase p equals 0 to p equal width of the matrix over the width of these tiles. So the first thing we're going to do is basically collaboratively load elements from the input in a tiled fashion into shared memory and then do a sync threads. So after that sync threads, we've got an entire tile of the input matrices in some very fast, on-chip shared memory that every thread in the block has access to. And then after that, it's just a very simple dot product across the shared array, just like we did in the previous kernel. The only difference here is that these loads are coming basically at the speed that we can access registers, so it's very fast. And then after we've done with our partial result for that phase, we do a sync threads to make sure that all the threads are ready for the next phase. Then finally, when that loop is done, we just write out the output as we did before. So just to take a look at that last implementation and provide some commentary on the use of those barriers. So you'll note that in each phase we use two barriers, right? We used the sync threads after we did this load, and then we did a sync threads after we did the reads from shared memory. And the idea here is that these barriers actually guard that memory to make sure that we don't corrupt it in the process of operation. So basically, we do that sync threads after we load all that memory, and then we do a sync threads after we've read all that memory from the shared array. And then note that that last sync threads there, that barrier guards the next phase. So basically, the idea here is to use barriers to guard against using data that's not been initialized or loaded yet, and also to guard against bashing data that's live or still needs to be used. And so you might ask yourselves, what's a good value for this constant tile width? How big should these tile sizes be? How big should our thread block sizes be? This is sort of the first time in the class we've started asking ourselves that question. So here's some first order considerations that we should have keeping in mind when we go into this implementation. First is that each thread block should have many threads, right? Because we'd like to maximize the amount of shared memory that we have access to because it's so fast, and we don't want to do all those redundant loads. And so if we choose a tile width of 16, that means our thread block size will be 256 threads per block. And then another concern is that, well, we want to have as many thread blocks as possible to basically fully occupy all the SMs on the machine. And you know, this tile width of 16 gives us this, right? Because if we assume that our matrix is maybe 1K by 1K, or 1 million elements total, so that implies if we use 16 by 16 blocks, that will end up with around 4,000 thread blocks, and that's plenty to totally fill up the machine, and we won't have to worry about underutilization of the SMs. And so basically, another nice property of this 16 is that this is going to give each SM 3 blocks to work on of 768 threads total, and this is going to totally occupy the SM, and there won't be any underutilized resources. And so finally, given this sort of magic number of 16 for our tile width, we can take a look at that ratio of bandwidth to flops, and you'll see that, well, each thread block is going to do 512 loads for basically 8,000 floating point operations. So no longer is bandwidth the limiting factor of this kernel. It's mostly limited by how fast we can do the math. And so let's just tabulate the results. So in our original implementation, if we counted up the number of loads we did, we see that that's actually 2 to the n cubed, or 2 times n cubed, right? We've got that extra n basically redundant loads. But in our improved version, we're able to reduce that down to 2 times n squared times n over the tile width. And you can see as tile width gets bigger and bigger, we're doing less and less redundant work, right? Basically, if we could fit the entire matrix into shared memory, we could implement this basically without doing any redundant global loads at all. And then we can take a look at the throughput of the 2 implementations. And so the throughput of that first naive kernel was only 10 gigaflops per second. It's pretty paltry, kind of depressing. But you know, just by thinking a little bit about the problem, tuning it to this particular machine, the improved version is able to get up to basically 80 gigaflops. And that's a 17x performance improvement. So I mean, think about what that means. 17x means you get to graduate your PhD maybe 6 months early, right? If you can crunch those dense matrices that much faster. And you can also look at the improvement on a per line of code basis. And basically, even if you divide that improvement by the number of extra, basically, implementation hours that you want to throw at it, we're still 8 times better than we were at the beginning. And so clearly, this optimization was worth the effort. We're still pretty far from the peak performance of this GPU. So in theory, we can do even better if we're willing to basically explore the optimization space further. And so you might ask yourself, well, what happens if we vary the tile size? What's the best tile size? And so what I did was I took these 2 kernels, basically varied the thread block size, and you can look at the results. So at the left here, we've got this untiled naive version that's performing at basically 10 gigaflops per second. And then to the right, I basically vary the size of the tile that I used in the improved implementation. And so using very small tiles is actually worse than no tiles at all. So 2 by 2 performs really poorly. And in fact, it's not until we get up to 4 by 4 tiles are we on parity with the original naive implementation. And you can see as the tile size grows, it gets a little bit better until finally there's this huge cliff at 16 by 16, right? The magic number. I was talking to David before class, and how do we explain this cliff, right? The example, I guess the first order explanation is that I don't really know why this cliff is there. To tell you the truth, I'm not an expert in dense matrix multiply, but to some extent, it's really not worth worrying about, I guess, because in an actual implementation, you would pay someone a lot of money to care about dense matrix multiply, and you would just ask him to please let me use your code. And in fact, there are standard libraries for doing this sort of thing. At least dense matrix multiply is not something you need to worry about too much.
If between the sidewalk. If you do 15, when you're copying, one thread is being idling, right?
Right, so the remark is, well, 16 by 16 gives you an integral number of warps, basically, right? So that's true. That's definitely important. Remember that the warp size on this architecture is 32. So if we make a thread block of 16 by 16, that'll give us basically, what, 8 warps, right? So that probably has something to do with it. Probably, I don't know, I guess David can comment on this further, but I think I'm just not going to speculate it on it. let's put it that way. People write academic papers on how these things perform. And so, to close up, you can, when thinking about these different memory spaces and the memory sources you have available on the GPU, you should realize is that these resources are finite, and they actually pose a limit to the parallelization that you can actually express and expect on the GPU. And I'll just give you a short example. So if we take a look at the number of registers that each streaming multiprocessor, or SM, has available, basically has 16,000 registers, right? And so to get to full occupancy on the SM, basically to launch a number of threads such that every thread is, or every computational resource on the SM is available, all the ALUs are utilized. To do that, that means basically you're limited to 768 threads to get all of those registers available to each thread. And that gives you 21 registers per thread. You basically get that by dividing 16,000 by 768. So I mean, that's not many registers to work with. And you can do the same kind of computation with the shared memory available to question. The question is, registers are 32-bit? Yes, they are. You can do the same math with shared memory. You basically you have the same, on the order of the same size, 16 kilobytes of shared memory per SM. That basically limits you, if you've got 8 blocks in flight on a particular streaming multiprocessor, that means each block only has access to 2 kilobytes of that shared memory. So at the end of the day, these resources are limited, and they're going to limit the number of threads you can launch at once per block. And you can make the general observation that the more memory addresses, basically, that each thread needs to access, that means that that's going to limit the number of threads that each SM can accommodate. So just some final thoughts. To get that actual effective and to get that peak throughput rate that is quoted on the side of the box, on the GPU at Best Buy, you basically need to make effective use of the memory hierarchy and the memory resources that are available. The sort of high order thoughts that you should take away from this talk is to basically use shared memory to eliminate these redundant loads from global memory. Because if you do all those redundant loads from memory, you're going to be bandwidth limited, and there's just not enough bandwidth to feed the peak arithmetic rate of the hardware. Use sync thread barriers to protect shared arrays, and use atomics if your patterns are sparse and unpredictable. As we noted, doing these optimizations typically tend to come with a development cost, so don't prematurely optimize. Ask yourself if it's really worth it. And finally, these memory resources are finite, and they're going to effectively limit the parallelism that you can expect to get at peak utilization. And so there's some tutorials up on the code site for the, thread local variables, shared variables, and then that matrix multiply implementation. If you want to publish a paper, get that matrix multiply code and make it 10x faster and graduate. So with that, I guess we can take questions, or we'll see you next time. Question? David, how close can we get it?
So I don't remember the exact number, but thankfully Niels has a laptop.
And
642 out of the 1 gigaflop for a slightly higher performance card. Is that?
yeah,
That's the
Yeah, that's the Volkov one, which is fastest.
Yeah, there's a really good, well, really detailed paper on this from a guy at Berkeley, Vasily Volkov, and in his paper, it's a slightly faster card, but he managed to get 624 gigaflops per second, and it's like a 12-page paper on all the optimizations he did to get there. So it's quite an interesting read.
So David, what do you think is an example of a kernel that would saturate peak throughput?
So there is a code from UIUC, I want to say, which does some a part of the molecular dynamics code, which it gets like 90-something% of peak.
And so the idea here is that this particular molecular dynamics code is compute bound, right? It's not bound by a memory.
Yeah, it's
all.
compute bound, and they have done, blocking out the wazoo and are using constant memory and shared memory.
Right.
And to, get enough bandwidth to feed the ALUs at the rate they need to. And they get exactly the right instruction mix and so on.
Quick question. In the case where all the threads are stalled on memory accesses, does prefetching make sense at all in the GPU, or does that not? Then it never.
I'll let David answer.
So prefetching can make a lot of sense. It depends a lot on your data access patterns and the number of your occupancy, basically. So if you are, every thread has its own access pattern, which you can predict, but they don't share, then often, so that some threads can kind of go ahead and grab a block and put it into shared memory, it might make sense. But at the same time, prefetching will kind of make your code more complex and increase your register count. So if you have, the maximum number of highest occupancy, it might actually not help at all. But I've seen lots of examples, and I've written several myself, where it does help a lot.
Are there directives in CUDA to move memory from global memory to shared memory without going through registers?
No, there's not. Shared memory is always completely under explicit programmer control. So you need to do that by hand.
Question?
Is there any way to dynamically find out how much shared memory is there?
Yes, so the question is, can you sort of divine the unique constants of your GPU at runtime? Like, can you ask how many registers do I have, how much shared memory? Yes, you can definitely do that. I believe the function is called CUDA get device properties, and it'll give you sort of a tabulated list of constants like that.
And just to add on, we're also going to show you partly in NP2 and partly just next week how many resources your actual kernel or kernels are using. Right? So you need both types of information. So that information is coming, and we'll show you how to get that.
All right, thanks everyone. See you next time.
For more, please visit us at stanford.edu.